Before we move into the bile part, I want you guys to know what bilirubin is. Now, whenever you get the breakdown of RBCs, which happens every 120 days, old RBCs are destroyed and they're destroyed by macrophages in the spleen or the liver, you get heme. Now, hemoglobin basically gives you heme, and heme gives you bilirubin. This is the big picture, right? Now, what happens is this unconjugated indirect bilirubin travels uh, in the blood, and basically since this unconjugated indirect bilirubin, it's not water soluble, so it travels in the blood while it's bound to albumin. So the bilirubin travels in the blood bound to albumin. Now this is transported to the liver. How is it transported to the liver? This unconjugated bilirubin plus albumin travels in the blood to the liver. Now, liver has the key processing step. What the liver does is basically it uses an enzyme called UDP glucuronyl transferase, the UGT. Let's go again. UDP glucuronyl transferase. Now, this is the main enzyme is in the liver, in the hepatocytes in the liver, and what this does is it takes this unconjugated direct bilirubin and converts it into conjugated bilirubin, right? So once it's conjugated, it becomes water soluble, right? Now it's called direct bilirubin. So once the glucuronosyl converts the unconjugated bilirubin, which was bound to albumin, into the conjugated direct bilirubin, now this is water soluble. So now we call it direct bilirubin. Now this bile, this conjugated bilirubin enters the bile. How does it enter the bile? It enters the bile in the hepatocytes. Now, once it enters the bile, it goes to the gut or the duodenum, right? So remember that once this goes into the bile to the duodenum, there's an intestinal conversion. In the intestines, this is converted further into urobilinogen. Now, urobilinogen has three fates. There are three things that can happen to the urobilinogen in the intestines. 90% is reabsorbed and it's returned to the liver and reused. 80% goes to stercobilin. Okay, and this gives the feces its brown color of the stool. And then 10% goes to the kidney. So you guys can see that 20% comes here. It's used in the stercobilin in the brown color of the stool, right? Here 90% is reused again. And of that, 10% goes to the kidney and gives the urobilin color to the urine. So this gives the yellow color to the urine, right? Now, let's go back and try to understand what bile is. Now, bile is this fluid which is composed of bile salts. Bile salts are basically conjugated to glycine or taurine to make it water soluble, right? Now, composition of bile is basically when you talk about bile, we have bile salts, we have bile pigments, we have cholesterol, fatty acids, lecithin, and mucin. This is part of the organic substance of the solid, and the inorganic substances include sodium, calcium, potassium, chloride, and bicarb. Now, what is the point of these bile salts? So, when you have this big fat globule coming in your food, ready to be digested, the bile salt emulsifies it. By emulsification, it means now when we talk about the bile salt, the bile acid part has two sides to it. It has a hydrophobic side which loves the fat, and it has a hydrophilic side that does not like the fat. It likes the water. The hydrophilic part likes the water. So, when a big lipid comes to the bile salts or bile acid, it gets attached to it by its hydrophobic side. Now, what does this basically do? It gives more surface area to the fat globule to be digested by the lipase and colipase by forming micelles. So, these micelles are like holding stations for the lipase to act on, right? So you have this fat that's entering the duodenum, these big fat hydrophobic clumped together particles, and then bile salts are released from the gallbladder, which is stimulated by CCK. And these bile salts have a hydrophilic side and a hydrophobic side. The hydrophobic side loves the water, loves the fat, and the hydrophobic side loves the fat and the hydrophilic side loves the water. So this hydrophobic side surround the fat and they help to break down these large globules into tiny droplets. This prevents a reaggregation of the fats together, so they can't clump around together. And this is called emulsification. So why is this important? It's important because pancreatic enzymes like lipase only work on the surface. So you need micelles, these holding stations, so that the pancreatic enzyme like lipase can work faster. After emulsification, pancreatic lipase breaks the triglycerides down into fatty acids and monoglycerides, which form the micelles. And these micelles are then absorbed in the small intestine. So you have these fatty acids and monoglycerides that are then formed into micelles, and then these are absorbed into the small intestine. Now, if you don't have bile, what happens is there's poor emulsification. And whenever you have poor emulsification, you have gallstones or bile duct obstruction, and this leads to fat malabsorption, which we call steatorrhea. Any pancreatic issues will cause, even if emulsification is fine, and there is no lipase, there's no digestion. So any pancreatic issue that is causing a decrease in lipase, you have no lipase, so there's no digestion, right? So that's something about the composition of bile salts. Now let's go and read what it says, that the bile salts are composed of bile acids that are conjugated to glycine or taurine, making them water soluble. We have phospholipids, cholesterol, bilirubin, and water and ions also. Cholesterol 7 alpha hydroxylase catalyzes the rate limiting step of bile acid synthesis. If you look at the bile acid synthesis, we can see that everything begins with a cholesterol in the hepatocytes, and then we enter the rate limiting step, which is uh, responsible by the 7 alpha hydroxylase enzyme. And this converts the cholesterol into 7 hydroxycholesterol. This is the most important step, and it controls the entire bile acid production. And then from here, you form the primarily bile acid. So you form the cholic acid, which forms the you form the cholic acid and the chenodeoxycholic acid here. These are the primarily bile acids that are made in the liver, and then further on conjugation makes them water soluble. So if you conjugate it with uh, glycine or taurine, that depends on what they further on form, right? So you get deoxycholic acid or lithocholic acid depending on whether you're conjugating it with taurine or glycine, right? So now something about the functions of bile. It's used in the digestion and absorption of lipids and fat-soluble vitamins, bilirubin and cholesterol excretion, body's primary means of elimination, and antimicrobial activity via membrane disruption. These are all the things that bile basically does. Now, you may have this question that how is bilirubin and bile connected? Now, I told you about the bilirubin. This conjugated bilirubin was secreted into the bile, right? And it was stored in the gallbladder and then released into the intestine. So, when the conjugated bilirubin is secreted into the bile, is stored in the gallbladder and then released into the intestine, this is the connection. The bile carries the conjugated bilirubin out of the body. So the intestines help to give this intestinal bile, which has the bilirubin in the gut. This helps to give the stool and urine the color, right? Now, bile is not just for fat digestion, it also protects the gut from unhealthy bacteria. So, the bile salts have amphipathic parts that are either fat and water loving. So, they insert into the bacterial membranes and they disrupt the bacterial membrane's lipid bilayer. And this leads to cell lysis and death of bacteria. So, bile salts dissolve bacteria like soap dissolves grease. And this prevents bacterial overgrowth, right? This is why small intestine has relatively low bacteria, because small intestine has a lot of bile. And this is why colon has high bacteria, because the colon does not have bile. This bile selects resistant bacteria. It only selects only bile resistant organisms are able to survive. For example, typhoid fever bacteria can survive bile because they infect Peyer's patches. Okay. Um, it basically, the bile works alongside the gut barrier of IgA, mucus, and peristalsis, right? So bile decreases bacterial overgrowth. Now we go on to this part where it says decreased absorption of enteric bile salts at distal ileum, which occurs in short bowel syndrome and Crohn's disease. Now, whenever you get Crohn's disease or short bowel syndrome, you have decreased absorption of enteric bile salts at the distal ileum, and of course, this will cause This will prevent normal fat absorption, and this may cause bile acid diarrhea. You may get fat malabsorption, you may get steatorrhea here. Calcium, which normally bind to oxalate, binds fat instead. So free oxalate is absorbed by gut. Now, what are they saying basically? What this is trying to say is that in fat malabsorption, you have fatty acids that are increased in the intestine because the fat is being malabsorbed. Fatty acids bind the calcium and form something called as the calcium soaps. Calcium is now very busy, so oxalate is left free. Since oxalate is left free, the free oxalate is absorbed by the colon, which is basically the gut. And now the colon, the oxalate in the blood leads into the oxalate being spilled into the urine because there's too much free oxalate, right? And that leads to increased frequency of calcium oxalate kidney stones. This condition is called enteric hyperoxaluria. Why the colon absorbs more oxalate is because there's so much free oxalate drying around, and normally the oxalate absorption is low, but the free oxalate is normally bound to calcium, but that is not happening here. So the colon permeability increases in inflammation, more oxalate enters the bloodstream. When is this seen? It's seen in Crohn's disease, it's seen in ileal resection or any short bowel resection or in bariatric surgery where there's fat malabsorption mainly. Okay, so you get calcium oxalate kidney stones here.